Okay, ladies and gentlemen, I would like to do a problem on internal forced convection, and it's from the textbook of Cengel and Ghajar, the 4th edition, and it is problem 8.39. The problem is an 8 meter long and uninsulated square duct of a cross-sectional area of 0.2 meters by 0.2 meters, and it has a relative surface roughness of 10 to the minus 3. It passes through the attic space of a house. Hot air enters the duct at 1 atmosphere and 80 degrees Celsius at a volume flow rate of 0.15 cubic meters per second. The duct surface is nearly isothermal at 60 degrees Celsius. Isothermal means constant temperature. The duct surface is nearly isothermal at 60 degrees Celsius, and determine the rate of heat loss from the duct to the attic space and the pressure difference between the inlet and outlet sections of the duct. Right, so the problem has already been summarized here on the board. It's problem 8.39 in the textbook of Cengel and Ghajar. Air, the temperature of 80 degrees Celsius and a pressure of 1 atmosphere, flows through a duct with a volume flow rate of 0.15 cubic meters per second. The surface temperature of the duct is approximately isothermal, so it's 60 degrees Celsius. The length of the duct is 8 meters. The surface roughness is 1 multiplied by 10 to the minus 3, and the geometry is 200 millimeters by 200 millimeters. So because the air is at a higher temperature than the air in the duct, the heat transfer rate would be from the inside to the outside. We have to calculate the heat transfer rate and the delta P, and also the fan power required. So we are working with air, and we will need the properties of the air, the average properties of the air through the duct. Normally we would like to have the bulk temperature, and the bulk temperature is the average between the inlet and the outlet temperature. We do not have the outlet temperature, so you can either guess maybe 70 degrees Celsius, or you can actually use 80 degrees Celsius, and then later on, when you have the outlet temperature, then you can get the bulk and you can just do the problem again. So let's start in this case with the bulk temperatures at 80 degrees Celsius. At 80 degrees Celsius, the density is equal to 0.9994 kilograms per cubic meters. The K value, the thermal conductivity, is equal to 0.2953 watts per meter degrees Celsius. The dynamic viscosity is equal to 2.097 multiplied by 10 to the minus 5. Cp is 1008 joules per kilograms degrees Celsius, and the Prandtl number is 0.7154. So all the properties that we might need. So in this case, we've got a square duct, and normally with all the equations that we have for the Reynolds number and the Nusselt number, it is based on a circular tube, a circular round tube. And we have to transform this geometry to that of a circular tube, and for that we use the concept of the hydraulic diameter, which you've already done in fluid mechanics. So the hydraulic diameter is 4 times the cross-sectional area divided by the perimeter, the wetted perimeter. 4 times the cross-sectional area, in this case, is equal to 0.2 multiplied by 0.2, divided by the wetted perimeter is 0.2, 0.2 plus 0.2 plus 0.2, so it is 4 times 0.2, and the result of that is 0.2 meters. So this square duct of 0.2 by 0.2 will have the same characteristics than that of a circular tube with an hydraulic diameter of 0.2 meters. Right, so we need to calculate the Reynolds number, and if we want to calculate the Reynolds number, we need the mass flow rate or we need the velocities. So let's do that quickly. We calculate the mass flow rate. The mass flow rate is equal to the density multiplied by the volume flow rate. The density is equal to 0.9994 multiplied by the volume flow rate, which is equal to 0.15, and the result is a mass flow rate of 0.1499 kilograms per second. Okay. Mass flow rate is approximately the same as the volume flow rate because the density is approximately equal to 1. So let's calculate the velocity of the air now through the duct. The mass flow rate is then equal to the density multiplied by the cross-sectional area multiplied by the average velocity. The mass flow rate is 0.1499. It's equal to the density, which is equal to 0.9994 multiplied by the cross-sectional area. And take note, this is the physical cross-sectional area, so that is not the cross-sectional area of a circular tube of 200 millimeters. It is still the physical problem, and that is equal to 0.2 multiplied by 0.2 multiplied by the velocity v, and from here we can solve the velocity v as equal to 3.75 meters per second. Okay. Right, so there we've got the mass flow rate now, and we've got the velocity. So we can calculate the Reynolds number. And to calculate the Reynolds number, there are at least 3 different methods that can be used. You can directly write it as rho multiplied by the velocity, multiplied by the hydraulic diameter, divided by the viscosity, which is then equal to the velocity multiplied by the hydraulic diameter, divided by the kinematic viscosity, or you can write it as 4 times the mass flow rate divided by the viscosity P multiplied by the hydraulic diameter, as we've derived previously in the lectures. So if we look at these possibilities, then we can see that we've got everything there except this viscosity. You can obviously go and calculate it quickly, and here we're the same. So what I'm going to do in this case is I'm just going to calculate the Reynolds number with that equation there, because it's going to be the less work. Right, so the velocity we have solved as 3.75 multiplied by the hydraulic diameter, which is 0.2, divided by the kinematic viscosity, which is equal to 2.097 multiplied by 10 to the minus 3. And from this, we can solve the Reynolds number as 35,765. A Reynolds number of 35,765. Now, that is larger than a Reynolds number of 2,300, which is the limitations between laminar flow and turbulent flow. So because it is larger than 2,300, we know that the flow is going to be turbulent. Right, now if the flow is turbulent, then if we go and calculate how long it will take before it is fully developed, it would be 10 times the hydraulic diameter. And in this case, it is 10 multiplied by 0.2, so it is 2 meters. So in terms of this total length of the duct, that is our total length of the duct, which is 8 meters. The first 2 meters, that is how long it will take before the flow is thermally fully developed and also hydrodynamically fully developed. Okay, so 2 meters. So that's about a quarter of the total distance. So in this, we know that if we plot the heat transfer coefficient as a function of x, that in this region, the heat transfer coefficient is going to be a constant, and there it is going to be a little bit higher. Now, we do have an equation where we can calculate that Nusselt number, but we do not have an equation that we can calculate this one with. So we will have to assume that the average heat transfer coefficient is going to be that value there, and we will have to take into we will have to always remember that it is actually a little bit higher. So we can calculate the Nusselt number for turbulent flow from the equation. It is equal, Nusselt number is equal to 0.023 multiplied by the Reynolds number to the 0.8 multiplied by Prandtl to the n. And the n is equal to 0.3 if we have cooling, and it is equal to 0.4 for heating. Okay. Now if we look at the air enters at 80 degrees Celsius and the attic is at 60 degrees Celsius, so the air will be cooled. So therefore n in this case is equal to 0.3. So let's calculate the Nusselt number. It is equal to 0.023 multiplied by the Reynolds number, which is equal to 35,765 to the 0.8 multiplied by Prandtl number, that is a bit in my way there, Prandtl number to the 0.3 because the air is being cooled. So from this we can calculate the Nusselt number as 91.4. Okay. The Nusselt number is the non-dimensional heat transfer coefficient. So the Nusselt number is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by K. So this is why we're using the hydraulic diameter, because now we can use the Nusselt number equations, and it is the same then with the Reynolds number there. So the Nusselt number we have calculated as 91.4 is equal to the heat transfer coefficient. That is what we want to calculate, multiplied by the hydraulic diameter, which is 0.2, divided by the thermal conductivity, which is equal to 0.2953. And from this we can calculate the heat transfer coefficient as 13.5 watts per square meter degree Celsius. Okay, so now we have the heat transfer coefficient, which is 13.5. And again, we remember it is for 6 meters of the tube. There it will be a little bit higher. We don't know what the value is. And again, what is also important to remember is that these heat transfer coefficients, the accuracy is about 20 to 40%. So in any case, it is not that accurate, but it's a good estimate. Right, so with this type of problem, what is very important to remember is that it is a problem where we have a constant surface temperature. So if we plot the temperature as a function of x, okay, then for the surface of the duct is going to be at 60 degrees Celsius, and it is going to be a constant. So there's 60 and there is 60. Well, the air is going to enter at 80 degrees Celsius and the temperature is going to decrease like that. We don't know this value there yet, but we need to calculate it. And we've already derived that for cases where we've got a constant wall temperature, then we can make use of the NTU method, the e to the minus NTU, to calculate the outlet temperature. And that equation we've derived previously, it is equal to the outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus NTUs. Okay, e to the minus NTU. We have to first, therefore, calculate the NTUs. The NTUs is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the Cp. The heat transfer coefficient we have solved as 13.5. This surface area will be a surface area where heat transfer will occur. So it is equal to 4 times 0.2, which is the perimeter of the duct, multiplied by the length of the duct, which is 8 meters, divided by the mass flow rate, which is equal to 0.149 kilograms per second, multiplied by Cp, which is 1008. So from this, we can calculate the NTUs is equal to 0.575. The NTUs is relatively low. If it would be equal to approximately 5, then this outlet temperature would be very close to 60 degrees Celsius. Okay. So it is less than 5, so it would be quite far from 60 degrees Celsius. So now we can calculate that outlet temperature from that equation. Let's just write the equation down again. So TE is equal to TS minus the inlet temperature, e to the minus NTUs. Okay. The surface temperature is equal to 60 degrees Celsius. The inlet temperature is 80, e to the minus NTUs, and the NTUs is equal to 0.575. So from that we can calculate the outlet temperature as 71.3 degrees Celsius. Right. So there's the outlet temperature as 71.3 degrees Celsius. Now we have to calculate the heat transfer rate, because that is one of the things that has been asked from us. And we can calculate the heat transfer rate from actually now two methods. The one is from the delta Tm method, which says that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by LMTD. Okay, what is this LMTD? The LMTD is a very good description of the average temperature difference between the surface and the fluid. Normally it wouldn't give good results if we would take the bulk temperature as the average between the inlet and the outlet and use that delta T as the average there. It is not going to give us very accurate results. So we have to use the LMTD. So let's calculate the LMTD. So the LMTD is this temperature difference, which is 80 minus 60, minus this temperature difference, 71.3 minus 60, divided by the ln of 80 minus 60 divided by 71.3 minus 60, and that gives us a temperature difference of, my goodness, no, I didn't write it down. What was it again, Marlies?
15.2383.
2383, is that right? Okay. Okay, so that is the LMTD, 15.2383 degrees Celsius. So now we can calculate the heat transfer rate as the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. The heat transfer coefficient is equal to, where is it now again? It is 13.5, is that right? Yeah, 13.5. There it is still on the board, multiplied by the area through which the heat transfer is going to occur. That is 4 times 0.2. 4 times 0.2 would give us the perimeter, multiplied by the tube length, which is 8, multiplied by the LMTD, which is equal to 15.2383. And from that we can calculate the heat transfer rate as 1,315 watts, or 1.3 kilowatts. That is the one method that we can use. The easier method would be just to look at the air side. On the air side, we have the mass flow rate multiplied by Cp multiplied by the inlet temperature minus the outlet temperature. So we can just look at what happens with the temperature drop of the air. There's a temperature drop from inlet to outlet multiplied by Cp multiplied by the heat transfer rate. So we could have directly calculated it from there. So the mass flow rate of the air is equal to 0.1499 multiplied by Cp is equal to 1008 multiplied by the inlet temperature is 80 minus the outlet temperature of 71.3. So that also gives us a heat transfer rate of 1,315 watts or 1.3 kilowatts or 32 kilowatts. So that is the heat transfer rate from the tube. We have also been asked to calculate the pressure drop. Okay, so we need to get the friction factor, and if we have the friction factor, then we can say that the pressure drop is equal to the friction factor multiplied by L divided by the hydraulic diameter multiplied by rho V squared divided by 2. Don't have the friction factor, so where do we get it from? Well, from the Moody chart. So if we go to the Moody chart, the friction factor as a function of Reynolds number, that is for the laminar flow regime, that is for a smooth tube. And if we go and look for the line where epsilon divided by d is equal to 1 multiplied by 10 to the minus 3, and we go and look at this Reynolds number that we've determined, of, what was it again, 33,765. 33,765. Then we can get the friction factor as 0.026. friction factor is equal to 0.026. Right, now we can calculate the pressure drop. Since we've got the friction factor, is equal to a friction factor which is equal to 0.026 multiplied by the length of the tube is 8 divided by the hydraulic diameter which is 0.2 multiplied by the density which is equal to 0.9994 multiplied by the velocity squared 3.75 squared divided by 2, and the result is a small pressure drop of 7.3 Pascal, but that is very normal for flow through ducts. Right, so that is the pressure drop, and then lastly we can also calculate the fan power, how much energy must be put into the air to get that flow rate through that tube, and we can calculate it as just the volume flow rate multiplied by the pressure drop. The volume flow rate has been given as 0.5 multiplied by the pressure drop, which is 7.3 pascals, and that would give us 0.095 watts. So a very small value that we need for the fan power. Right, thank you very much.